In the late 1950s, the United States possessed the most powerful military machine in human history. Its Strategic Air Command could darken the skies with jet-powered bombers. Its army was deploying the first generation of intercontinental ballistic missiles. On paper, the American nuclear deterrent was an invincible triad of land, sea, and air power, designed to guarantee that no enemy could ever launch a surprise attack without facing total annihilation. But this image of invincibility masked a dangerous reality. The triad, as it existed, rested on a glass jaw. Its bombers were parked on known, vulnerable runways. Its first-generation missiles were liquid-fueled rockets that took hours to prepare, sitting in known fixed locations. The entire multi-billion-dollar apparatus of American survival was dangerously exposed to a single, decisive Soviet first strike. Washington was in a strategic panic. The launch of Sputnik in 1957 had proven the Soviets possessed the rocket technology to bypass America's oceans. While the U.S. still held the numerical advantage, the vulnerability of its forces was a mathematical reality. If the Soviets struck first, the United States might not have a sword left to swing back. The solution to this existential crisis would not come from a bigger bomber or a thicker concrete silo. It would come from the sea. It would require a team of naval officers and engineers to solve 4 impossible engineering problems simultaneously. They would have to invent a new kind of nuclear warhead, a new kind of rocket fuel, a new way to navigate without stars, and a digital brain capable of thinking in 3 dimensions. This is the story of the Polaris program. It is the story of how the Navy took a nuclear reactor, cut a submarine in half, and stuffed it with solid-fuel rockets to create the most destructive, stealthy, and stabilizing weapon system ever built. It is the engineering miracle that terrified the Kremlin and froze the Cold War.
To understand the sheer magnitude of the Polaris engineering achievement, one must first understand the desperate fragility it replaced. In 1958, the United States' nuclear posture was based on the concept of massive retaliation. But retaliation requires survival, and every existing leg of the US Nuclear Triad was dangerously exposed. The primary instrument of American power was the Strategic Air Command, or SAC. Its fleet of B-52 Stratofortresses and B-47 Stratojets formed the visible arm of deterrence. These were technological marvels, capable of carrying megaton-class weapons across continents. But their vulnerability was not in the air, it was on the ground. The entire SAC fleet was concentrated on a handful of air bases. These locations were fixed, known to Soviet intelligence, and completely unhardened. A 1959 analysis exposed the terrifying mathematics of this vulnerability. In 1957, the Strategic Air Command estimated that a Soviet surprise attack could destroy 85% of the bomber fleet on the ground within 15 minutes. A small number of warheads detonated over the parking aprons would wipe out the force before it could even taxi. This created a use-it-or-lose-it posture. The entire deterrent depended on a warning time of only a few minutes. In a crisis, the president would face incredible pressure to launch the bombers immediately based on imperfect radar data, simply to prevent them from being destroyed on the ground. This was not stability, it was a hair trigger. The second leg of the triad, the land-based ICBM, was intended to solve this problem. Instead, it compounded it. The first generation of American missiles, the SM-65 Atlas, were rushed into service in 1959. These missiles were housed in hardened silos constructed by the Army Corps of Engineers. But hardened is a relative term. These early silos offered protection against overpressures, of only 100 psi. They were vulnerable to any near miss. But the fatal flaw of the Atlas was its chemistry. These rockets used cryogenic liquid propellants, RP-1, a refined kerosene, and liquid oxygen, or LOX. Liquid oxygen is a nightmare substance. It boils at minus 297 degrees Fahrenheit. It cannot be stored inside the missile for long periods. It boils off and freezes valves. Before an Atlas could launch, the crew had to pump thousands of gallons of supercooled oxidizer into the missile. This process took anywhere from 15 minutes to an hour. During this fueling sequence, the missile was defenseless, and the silo was a frantic hub of activity. Like the bombers, the Atlas silos were fixed targets. A Soviet planner knew exactly where they were and knew that the Americans needed 30 minutes to fuel them. This made the Atlas a first strike weapon by necessity. It was only useful if you fired it before the enemy fired theirs. As a retaliatory weapon, it was an iron coffin. The obvious solution was to move the missiles to sea. The ocean is vast, opaque, and constantly moving. A missile hidden in the ocean is immune to a preemptive strike. But the Navy's first two attempts to achieve this were catastrophic failures, proving just how difficult the engineering challenge really was. The first attempt was the Jupiter missile. The Navy was forced into a partnership with the Army to adapt this land-based intermediate-range ballistic missile for ships. The program was doomed by physics. Like the Atlas, the Jupiter used liquid oxygen. The handling of volatile cryogenic liquid oxygen within the confined pressurized hull of a submarine was deemed an unacceptable hazard. The risk of explosion was tantamount to suicide. The Navy rejected the Jupiter not just because it was dangerous, but because it was operationally useless. To fuel the missile, the submarine would have to surface and sit exposed in the waves, pumping explosive liquid while enemy radar hunted for it. The second attempt was the Regulus. This was a turbojet-powered cruise missile deployed on 5 submarines between 1955 and 1964. While safer than the Jupiter, the Regulus was a tactical disaster. It was a subsonic missile that required radio command guidance. To launch a Regulus, the submarine had to surface. It had to drag the missile out of a hangar, mount it on a rail, and fire it. But the vulnerability didn't end there. Because the missile needed guidance commands, the submarine had to stay on the surface, broadcasting a high-power radio signal to the missile for its entire flight, potentially 30 minutes or more. A regular submarine, by the very act of executing its mission, became a radio beacon. It broadcast its precise location to every Soviet anti-submarine warfare asset in the North Pacific. It was a sitting duck system that sacrificed the submarine to launch the weapon. By 1956, the strategic picture was bleak. The bombers were vulnerable on the ground, the land missiles were slow to launch, and the sea-based missiles required the submarine to surface and die. The U.S. needed a weapon that could be launched instantly from a submarine that remained submerged, undetectable, and safe. To the engineers of the day, this set of requirements sounded like science fiction.
The solution to the vulnerability crisis would not come from a single invention. It required a cascade of engineering miracles, where 4 distinct, impossible technologies had to be invented and perfected simultaneously. To manage this chaos, the Navy created the Special Projects Office, or SPO, in 1955. They placed it under the command of Rear Admiral William F. "Red" Raborn, a charismatic and ruthless manager who was given a blank check and an impossible deadline. His task was to invent the future before the Soviets could build enough missiles to destroy the present. The entire Polaris program was unlocked by a breakthrough not in rocketry, but in nuclear physics. The primary constraint on a submarine missile is size. It must fit inside a hull. Solid fuel, which is safer than liquid, is also less efficient. It has a lower specific impulse. To lift the massive hydrogen bombs of the mid-1950s, a solid fuel rocket would have to be enormous, too big for a submarine. The deadlock was broken in the summer of 1956 at a secret study group known as Project Nobska. There, the physicist Edward Teller, the father of the hydrogen bomb, dropped a bombshell of his own. He told the Navy that warhead technology was moving so fast that a drastic reduction in size and weight was imminent. Why use a 1958 warhead in a 1965 weapon system? Teller argued the Navy could soon have a powerful warhead that was small enough and light enough to sit atop a compact, solid-fuel rocket. This was the key. By shrinking the warhead, the Navy could shrink the missile. The physics breakthrough enabled the propulsion revolution. With the weight requirement dropped, Lockheed engineers could abandon the suicidal liquid fuels and focus on miracle number one, the solid fuel motor. The technology they perfected was a composite propellant. This was not gunpowder. It was a stable, rubbery mixture. It consisted of three main parts. First, the oxidizer, like powdered ammonium perchlorate. Second, the fuel and binder, a polymer resin that held the mix together. Third, the accelerant, powdered aluminum, to raise the burn temperature. The genius was in the manufacturing. Liquid fuel is pumped. Solid fuel must be cast. The engineers developed a method to mix this slurry and pour it into the motor casing, curing it into a single monolithic block called a grain. But it wasn't just a solid block. They cast the core in a precise star-shaped geometry. This increased the surface area, allowing the fuel to burn inside out at a precisely calculated rate. This casting process was critical. It eliminated the microscopic cracks and air bubbles inherent in older techniques, cracks that would cause a motor to overpressurize and explode. The result was a motor that was stable, shockproof, and ready to fire instantly even after sitting in a submarine for months. But having a rocket was useless if you couldn't fire it. Igniting a 30-ton solid-fuel rocket engine inside a submarine would, in the words of one engineer, incinerate the boat and everyone inside it. Yet the boat could not surface. The solution was the miracle number two, the cold gas launch. Lockheed engineers realized they shouldn't treat the Polaris as a missile, they should treat it as a torpedo. They developed a system that used a massive gas generator to eject the missile from the tube without igniting the motor. The gas generator activates, instantly pressurizing the base of the tube. The 30-ton missile is punched out of the submarine, accelerating up through the water column like a massive dart. It breaches the surface solely on momentum. Only when the missile was airborne and a safe distance from the submarine would an internal accelerometer sense the change in gravity and ignite the first-stage motor. This decoupled the violence of the launch from the safety of the platform. The submarine remained submerged, silent and cold, while the missile roared into the sky. A ballistic missile is a blind robot. To hit a target in Moscow, it needs to know two things: where Moscow is and exactly where it is at the moment of launch. For a land-based silo, this is easy. The silo doesn't move. For a submarine, it is a nightmare. A submerged submarine is blind. It cannot see the stars for celestial navigation. It cannot raise an antenna for GPS or radio fixes without revealing its location. If the submarine is off by 1 mile in its own position, the missile will miss the target by 1 mile. The solution was the miracle number 3, the ship's Inertial Navigation System, or SINS. Developed by the legendary MIT Instrumentation Laboratory, SINS was a mechanical inner ear for the submarine.
It consisted of a platform isolated from the ship's movement by servos, holding ultra-sensitive gyroscopes and accelerometers. SINS feels every motion. It feels the submarine turn, accelerate, dive, and rise. By continuously mathematically integrating these motions, the computer can calculate the ship's position relative to its last known point, without ever looking outside. This was the true key to invulnerability. The solid fuel made the missile safe. The cold launch made it fireable. But SINS made the submarine invisible. It untethered the boat from the surface. A Polaris submarine could dive and disappear for months, maintaining a perfect firing solution without ever exposing a periscope to get a fix. The final miracle was the missile's own brain. The German V-2 rocket used analog guidance, simple gyros that tried to keep the rocket on a preset curve. If wind or vibration knocked it off course, it simply tried to get back to the old line. But a submarine launch is chaotic. The boat is pitching and rolling in the ocean currents. The missile is ejected through turbulent water. No two launches are the same. An analog system couldn't cope. The Polaris needed a computer that could think. The result was one of the very first digital guidance computers ever placed on a missile. Also developed by MIT's instrumentation laboratory, this compact device was a direct precursor to the Apollo guidance computer. It didn't just follow a path, it calculated one. At the moment of launch, SINS uploads the precise coordinates to the missile. Once airborne, the missile's computer senses its actual velocity and position. It doesn't try to return to a pre-programmed path. It calculates a brand new, optimal trajectory to the target from wherever it happens to be. This digital flexibility meant that a Polaris missile could be fired from a moving platform in rough seas and still find its target with devastating accuracy. These four miracles, the warhead, the fuel, the launch, and the guidance, needed a home, and Admiral Raborn needed it now. He didn't have time to design a new submarine hull. In a masterstroke of kit bashing, the Navy took the hulls of Skipjack-class attack submarines that were already under construction on the slipways. They literally cut these hulls in half. Into the gap, they welded a new 130-foot-long missile compartment. The crew called it Sherwood Forest. It was a cavernous compartment dominated by 2 rows of 8 vertical launch tubes, 16 trunks of steel, painted forest green. This act of industrial surgery created the George Washington class. It was the world's first true ballistic missile submarine. It was a submerged missile silo, a weapon system that combined the unlimited endurance of a nuclear reactor with the infinite concealment of the deep ocean. And it went from a paper concept to a commissioned warship in just 4 years.
Solving the physics of the Polaris was only half the battle. The other half was the war in Washington. The Polaris program was a managerial monstrosity. It involved an estimated 11,000 different contractors, from massive aerospace giants to tiny electronics workshops. It required the coordination of dozens of government agencies, and it was born into a shark tank of inter-service rivalry. The U.S. Air Force viewed the Polaris program as a mortal threat. They saw strategic nuclear bombing as their domain. Every dollar spent on a submarine missile was a dollar taken away from their bombers and their Atlas silos. They were looking for any excuse, any delay, any cost overrun to kill the Polaris program in Congress. To protect his engineers, Admiral Raborn needed a shield. He needed a way to keep the auditors, the congressmen, and the Air Force generals at bay. He needed a weapon of bureaucracy. And so, the Special Projects Office invented one. They called it PERT. PERT stood for Program Evaluation and Review Technique. It was a revolutionary project management tool developed inside the Navy's Special Projects Office in collaboration with Booz Allen Hamilton and Lockheed. It was a system of complex network flowcharts. It mapped every single one of the millions of tasks required to build the submarine, identifying the dependencies between them. It famously used 3 time estimates for every task: optimistic, pessimistic, and most likely. By feeding this data into a computer, PERT could supposedly identify the critical path, the specific sequence of tasks that determined how long the project would take. The story told to the public and to Congress was that PERT was the magic wand. It was the super tool that allowed the Navy to herd 11,000 contractors and finish the program 3 years ahead of schedule. It became a legend in management science, taught in business schools for decades. But there is a twist. In 1972, an MIT political scientist named Harvey Sapolsky conducted a deep audit of the program. He interviewed the managers and read the internal memos, and he found the truth. PERT never played the role in Polaris that it is generally claimed to have had. It was not used for day-to-day decision-making. The technical teams building the missile didn't run the program by looking at PERT charts. They just did the work. The true function of PERT was not logistical. It was rhetorical. It was a bureaucratic shield. Admiral Raborn realized that in the Pentagon, complexity looks like competence. When the Air Force or Congress demanded an audit, the Special Projects Office would roll out a 50-foot-long PERT chart. It was covered in arcane symbols, computer punch card data, and statistical probability curves. It was dazzling. It was overwhelming. It terrified the auditors. No one wanted to argue with the computer. The sheer visual complexity of PERT created an appearance of unique managerial competence. It convinced the politicians that the Navy knew exactly what it was doing, down to the minute. The result was hands-off treatment. The Air Force couldn't find an angle of attack. Congress kept signing the checks. PERT bought the engineers the one thing they couldn't invent: autonomy. The greatest trick of the Polaris program wasn't the solid fuel or the guidance system. It was a management flowchart that successfully engineered the American political system.
On November 15, 1960, the USS George Washington slipped beneath the Atlantic and disappeared on the world's first deterrent patrol. The game had changed. The U.S. had achieved a cascade of convergent innovation that the Soviet Union could not match. The Kremlin, terrified by this invisible threat lurking on their doorsteps, was forced into a desperate, rushed, and imitative response. This response reveals the true extent of the U.S. engineering victory. While the Americans had invented a new kind of warfare, the Soviets were forced to cobble together dangerous compromises. The first Soviet attempt was the Project 658, known to NATO as the Hotel-class. Deployed in 1960, it was a Frankenstein's monster of a submarine. The designers took the hull of an existing attack submarine and crudely welded a missile compartment into the sail. It carried only 3 missiles to the George Washington's 16. But its fatal flaw was the launch procedure. The Hotel-class had to surface to fire. The launch evolution took 12 minutes on the surface. In modern warfare, a submarine that spends 12 minutes on the surface is a submarine that is already dead. This was a strategic failure. The Soviets had effectively rebuilt the obsolete American Regulus system, just as the Americans were abandoning it.
But the failure wasn't just strategic. It was physical. The rushed engineering of the Hotel class led to the infamous K-19, known to its crew as Hiroshima. The K-19 suffered a catastrophic reactor coolant failure on its maiden voyage in 1961. The crew was forced to enter the reactor chamber without protective gear to weld a cooling pipe. 8 men died of acute radiation poisoning within weeks. 14 more would die in the following years. In total, 22 men sacrificed their lives to save the ship. The Hotel class was not a deterrent. It was a radioactive trap for its own sailors. It wasn't until the late 1960s that the Soviets fielded a true competitor, the Project 677A, or Yankee-class. On the outside, it looked like a direct copy of the American boat. It had 16 missile tubes behind the sail. It was nuclear-powered. It could launch while submerged. It looked like parity. But looks were deceiving. Under the skin, the Yankee-class suffered from 2 fatal engineering flaws that made it a lesser weapon and a greater danger. The first flaw was fuel. The Americans had mastered safe, castable solid fuel. The Soviets had not. Their R-27 missiles used liquid fuel. But not cryogenic oxygen. They used storable hypergolic propellants, nitrogen tetroxide and UDMH. These chemicals are nightmares. They are toxic, corrosive, and they ignite instantly on contact with each other. The US Navy had rejected liquid fuel as unacceptable. The Soviets filled their submarines with it. The design flaw lay dormant for years, but the debt was finally collected on October 3, 1986, aboard the Yankee-class sub K-219. While on patrol off Bermuda, a seal on a missile tube failed. Seawater rushed in. When seawater mixes with liquid rocket fuel, it creates nitric acid and intense heat. The resulting chemical explosion ejected the missile and its warheads into the sea and ruptured the hull. The K-219 sank. The Soviet reliance on liquid fuel turned their own missiles into ticking time bombs. The second flaw was tactical. The Yankee-class was loud. U.S. attack submarines, maintained with fanatical attention to silencing, could detect a Yankee from miles away. American sonar operators could often identify individual Soviet ships by the unique acoustic portrait of their rattling machinery. Worse, the Soviet missiles had short legs. The Yankees' missiles had a range of only around 1,500 nautical miles, compared to the Polaris A-3's approximate range of 2,500 miles. This geometry was fatal. To hit targets in the U.S., the Yankee submarines couldn't hide in the deep Atlantic. They had to come close. The short range forced the Soviet fleet into predictable patrol boxes just off the U.S. coast, east of Bermuda and west of California. The U.S. Navy knew exactly where to look. These boxes were monitored 24/7 by P-3 Orion aircraft and the SOS-US underwater listening network. The Yankee-class was not a hidden deterrent. It was a tethered one. The Soviet Union had built a fleet of submarines that were loud, prone to exploding, and forced to operate in a shooting gallery controlled by the U.S. Navy.
The deployment of the 41 for Freedom, the 41 ballistic missile submarines built by the United States between 1959 and 1967, fundamentally altered the physics of the Cold War. Before Polaris, nuclear war was a race of who could strike first. After Polaris, striking first was suicide. The value of this second strike capability was proven in the fires of October 1962. During the Cuban Missile Crisis, the world stood on the razor's edge. The Air Force generals pushed for a first strike. The Soviet generals pushed for a first strike. But beneath the waves, 5 Polaris submarines were on patrol. They held 80 nuclear warheads on silent alert. Soviet Premier Khrushchev knew this. He knew that even if his missiles in Cuba wiped out every SAC base and every Atlas silo in America, the Polaris boats would rise from the ocean and destroy the Soviet Union. This was the ultimate leverage. The Polaris fleet was the only part of the arsenal that didn't face the use it or lose it pressure. It gave President Kennedy the confidence to wait, to negotiate, and to de-escalate, knowing his ultimate trump card was safe underwater. The engineering miracle of Polaris also reshaped the map of Europe. In 1962, the U.S. canceled the Skybolt missile, leaving the British government, which had bet its entire nuclear future on it, in a crisis. Prime Minister Harold Macmillan's government was on the brink of collapse. At a tense meeting in the Bahamas, President Kennedy made a historic offer. He offered to sell the Polaris system to the United Kingdom. The Nassau Agreement saved the British deterrent and cemented the Royal Navy's focus from battleships to ballistic missiles. It cemented the special relationship, creating a technological bond between the U.S. and UK submarine forces that operates to this day. The impossible engineering of 1960 never went away. It evolved. The Polaris A-1 was a city killer, accurate enough to hit a metropolis, but not a hardened silo. Over the decades, the system was refined. First came Poseidon in 1971. It introduced the MIRV, multiple independently targetable re-entry vehicles. A single missile could now split into 10 or 14 separate warheads, overwhelming any defense. Then came Trident in 1979, extending the range to cover the entire globe. Today, the Ohio-class submarines carry the Trident II D5. It is the direct, linear descendant of the Polaris, but it has perfected the mission. The Trident has the accuracy of a land-based missile with the invulnerability of a submarine. It provides a counter-force capability, meaning it's capable of destroying hardened enemy silos with pinpoint precision. The Polaris program began as a desperate attempt to fix a glass jaw. It ended up building an indestructible shield. By solving the impossible problems of fuel, guidance, and navigation, Admiral Raborn's engineers removed the incentive for a surprise attack. They turned the ocean into a sanctuary, and in doing so, they ensured that the Cold War remained a war that no one could win, and therefore, a war that no one would start. The legacy of Polaris is not just a machine. It is the silence of the deep and the uneasy peace that has held for 60 years.